So what do students do? So the first, before we can answer that, we have to think about what they need to know by the time they finish. But we asked industry, what sort of things our graduates need to know and be able to do? And this is what they told us. This is a summary of what employers of engineering graduates told us. I'm going to start with 2 domains of knowledge. Here's the first one. Awareness and understanding of these things: human, social, political, economic, business, medical and environmental sciences. Not things you normally associate with engineering. But these are the things that engineers have to know about this stuff before they can do engineering. They have to know about the world they live in, the people that live in it, the problems they face, the things they'd like to be able to do, before they can even start any engineering. And here's the stuff we expect engineers to have, that I'm sure you already had in mind. This is the techie stuff. Expertise in maths and physics, basically. Maybe a bit of biology, a bit of chemistry. The engineering sciences, they're the things we teach you here. Thermodynamics, aerodynamics, structural dynamics, solids, materials, all the advanced engineering sciences. And then here, we've got some of the main tools used in engineering: simulation, experimentation and analysis. So, touchy-feely, human-y stuff, techie stuff, 2 main domains of knowledge. And then they need to be able to use that knowledge to do this. These blue boxes are my effort to capture what engineering is. Conceive, design, develop, invent, in other words, manufacture and supply, make, use, and then get rid of at the end of life. To do all that properly, they need to be good at these things: management of the creative process. Project cost and risk management speaks for itself, and interdisciplinary collaboration. Engineers have to work with different types of engineers. The manufacturing engineers, for instance, will have to work with mechanical and materials engineers. But then outside the discipline, engineers have to communicate with the people that they serve. The medics, for instance, we've touched on that, haven't we? I told you how there would be no Royal without engineering. No Royal Hospital without engineering. Engineers have to work very closely with the doctors or other healthcare professionals to understand what they need, so that then they can design, develop and put it in the hospital. Okay, and to do all that stuff, engineers need to be, and this is true, of all the graduates of this university, the most sophisticated communicators and team workers are the engineers. So the question is, what do students do, and is it good fun? Okay, so here we go, the lecture. About 15 hours a week in year 1. In every subject, in every country, in every university around the world, the lecture is the most common learning experience. Okay. So loads of students in the audience, one person like me at the front, talking for 1 or 2 hours. You can imagine how boring that is. We've been going for about 25 minutes, I'm sure you're getting a bit bored already. And sitting there on your backsides listening to me like that, like you are now, it certainly doesn't do anything to help you develop all those skills that we saw are so important. So really, no university education should centre around the lecture, but especially not engineering, where you have to be able to do so much stuff. So, we do start with lectures, 15 hours a week in year 1, as you saw. That goes down very quickly in year 2, and by year 3 and 4 you're spending less than half your time in lectures, much less. Most of your time there you're spending in teams, doing stuff together, being engineers. We've got an Ask the Audience system. Every student gets one on day 1, and they give it back to us when they leave. And basically, it's exactly Who Wants to Be a Millionaire? Ask the audience. So, I could stop now, you're all looking a bit tired, looking like you're fed up with listening to me, and ask you to do something. It might be a calculation, based on some science we've just covered. And then I'll ask you to give me an answer, A, B, C or D, on the touchpad. So we've had a break. And then I ask you for your answers, and immediately I get a histogram on the board, which tells me how many of you got it right. And those of you who've got it wrong, where you got it wrong. But this allows me to see, actually 80% of these students haven't got the principle of conservation of momentum. I've taught that wrong. I'll have to go back and do it again. But if 80% got it right, I can move on, I'm quite happy. And I can deal with the 20% offline after the lecture. So, that's a good thing we do. Experiments, you'll be familiar with this, doing physics. You do some stuff in the classroom where you learn about theory, but then you go into a lab and you prove it for real. And we do the same here. It's the way that people's minds work. Often you don't really get to grips with this principle until you've seen it in action. Okay, that's the sciencey bit. The engineering bit starts in year 1, week 11. Students come in expecting a normal week and they get the surprise that everything's been cancelled. This week there's no lectures, there's no tutorials, there's no labs. What you're doing instead is working with this team of 6 people, you might not know. And you've got 1 week to, in this case, design and develop a water-powered rocket. We'll come back in 5 days' time and assess you on how well you've done. Here's a more advanced one. Again, timetable cancelled. Students here designing remotely controlled aircraft. This aircraft's in a wind tunnel, instrumented up, and on their screen they're capturing data which they'll use with their scientific knowledge to design the aerofoil. A bridge, again, basic structures. Students have worked as a team together. They're now presenting it orally to this guy, who's one of the tutors, performance of the design and function of their bridge. So they're being practical, they're applying science to develop things, and they're doing it with each other, and they're having to plan, manage, organise and report on their own work. This is behaving exactly as a professional engineer does. Semester 1. There's another one, Lego. Very simple way of getting students to be able to make their designs. In this case, it's a wind-powered car which drives into the wind tunnel. Civil engineers, it's very difficult. Civil engineers make buildings and roads and stuff. Very difficult to do that in a lab here. So our second year students go to basically a flat field in windy East Anglia, which is called the National Construction College. And they go there with engineering contractors, the people with the diggers and the cement mixers and the bulldozers and stuff. And with the civil engineers, the likes of Arup, the big companies that design buildings. And they work to build tent-scale replicas of iconic engineering buildings. So this year, they built the Gherkin in London, they built a section of the Millau suspension bridge in France, and they built an oil rig. And when I say built, they start with a field of mud. Our students mark it out, dig the foundations, pour the concrete, put up the steelwork, do everything themselves. And all the planning and management of that. So this is really being a civil engineer with real civil engineers. Heavy lift aircraft, again I'm going to speed up now. So this was an international competition to build an aircraft which would carry most water around the route and into a cylinder at the other end. So designed it from scratch using a lot of engineering science. We did ours with a Portuguese university here in collaboration with them. We entered the competition 3 weeks ago at a windy airfield in York, and we beat the Germans in the final. So we won this for the first time. We're very proud of that. Okay, and here's really the pinnacle of our student practical engineering. You might have seen this car, you didn't get in the foyer, did you? You might see a car like this on your tour around the department. Each year at Silverstone, the week after the British Grand Prix, is the annual World University Grand Prix. It's called Formula Student. There's 100 teams from 30 countries, about 30 teams from this country there. And the students design and build their own car each year from scratch. They're given an engine, 600cc motorcycle engine. For everything else they design and build themselves using everything they've learned over 4 years of studying engineering. 35 students on the team, 450 hours each. So a lot of work goes into this thing. That's what they get credit for. They actually probably double that, some of them, to get it done in time for the race. So it goes 0 to 60 in 4 seconds, which is quite frightening in any car, but when your bum's that far off the floor in something the students have built, it's very frightening. You wouldn't catch me in it. Okay, but it's competitive racing, but also the design of the car is gone over in fine detail by automotive engineers, and it's a business game as well. So they've had to develop a business plan about the development and sale of their car. So this is a holistic approach to engineering, and if you're good at this, it shows employers shorthand that you're the person they want working for them.